Okay, so we kind of finished up bonding yesterday. So today we're going to actually go back to chapter 3, and I think it's sort of the last section of chapter 3, which is about naming. So we're going to talk about obviously all the different types of naming that you'll be responsible for, and then I believe that will go into the study assignment for today. All right, so nomenclature obviously is naming, and an important part in naming is ionic compounds, and ionic compounds are really always sort of a metal and a non-metal. And the other type of naming is really covalent compounds, like we talked about with bonding. So we're obviously going to talk about ionic compounds, which once again, as we talked about, is always a metal and a non-metal together. And always in this case, we get a transfer of the electrons from the metal to the non-metal. The result of that is kind of important for naming as well, is we do create ions. So we create cations out of our metal, which are positively charged. We create anions out of our non-metal because they gain the electron and they are negatively charged. Once again, as we talked about in bonding, they're obviously not, there's no sharing of electrons here, just a transfer of electrons. And the other type of sort of naming we'll talk about is molecular or covalent compounds, or molecular. And these guys are usually between two nonmetals or more. And here we do have obviously our sharing of electrons. So really helpful in sort of naming is sort of identifying obviously the type of compound that you're going to be naming, and obviously following the specific rules. So when we talked about sort of the periodic table and we talked about ions, again, especially important here for bonding, not bonding, but for naming, is the fact that there are certain things on the periodic table which have basically fixed charges. So everybody here in group 1 has a +1 charge. So again, no matter the situation, they will always form that +1 charge. As we talked about with the periodic trends, really because, at some point they're going to get into those core electrons, they're not going to be removed. So they're only going to remove really those valence electrons, which will get you to that +1 charge. Group 2 here is +2. So everybody there in group 2 will form a +2 for the exact same reason. Again, past the second electron into those core electrons, not going to really happen. As we sort of transfer over to our right-hand side here, group 3, and it's really, for the most part, aluminum there is going to be +3. Gallium is +3, can occasionally be something else, but really aluminum there is going to be +3. So that's sort of where our metals sort of lay up there in terms of those guys. We have our staircase, which above our staircase, I'll spit that out, above our staircase there is the non-metals, and those are, again, guys going to gain electrons. So there's not a really great pattern here in group 4, but starting in group 5, and again, these refer obviously to our non-metals, they make a -3 charge. So that's your nitrogen, phosphorus, and so forth. -2 there in group 6, oxygen, sulfur, selenium, and -1 there in group 7. So your fluorine, your chlorine, your bromine, all those guys. So these guys are pretty much fixed charges. We always know that this is the charge that they're going to make. And that's really different than pretty much a majority of what's left over, which is the transition metal region. For the most part, everybody in this sort of transition metal region, and a little bit outside of the transition metal region, underneath the staircase and sort of this region as well. Again, those guys are metals underneath that staircase, so they actually will make a positive charge. Those guys can have a variable type of charge, so they can make different types of charges in that sort of area as that transition metal region, and a little bit to the right of it has variable charge. There are sort of 3 exceptions that we commonly come across that, although they are sort of transition metals, they still actually have sort of fixed charges. And those are sort of this backwards L that's sort of right about here, coming this way and this way. So these guys here have basically fixed charges, even though they're transition metals. Zinc and cadmium will always be +2. So zinc and cadmium always +2. And our silver here will be +1. So this is really important, obviously, for naming and writing correct formulas, is to know the charges of things. It helps you sort of get the right name if you need to. Also put the formulas together correctly. Any questions on that there? Okay. So let's talk then first about really ionic compounds. And ionic compounds obviously contain ions. And when we talk about ions, again, we have our cation, which are positively charged, and we have our anions, which are negatively charged. So if you have just the formula of an ion, either a cation or an anion by itself, the way we go about naming them is a little bit different for each of them. If you have any type of cation, like H+, that is what is known as the hydrogen ion. If you had something like Li+, that would be the lithium ion. Yeah, some magnesium, Mg2+ would be the magnesium ion. So the nice thing about sort of the positive guys is in terms of the ion name, you pretty much just use the whole name of the element, whatever it may be, and you stick ion at the end of it. Anions are a little bit different. Anions, we sort of use the root of the name, but we do change the last part, and they get the IDE sort of ending to it. So if we had something like H-, which is sort of the negative form of hydrogen, that would be hydride. And hydrogen is one of the only ones that could kind of go both ways, positive or negative. If we had something like Cl- instead of chlorine, this would then become the chloride, IDE ion. O2- instead of oxygen would become the oxide ion. So pretty much metals, positively guys, just the whole name of the element. Negative guys get the IDE at the end of it. And that's sort of how we go about naming just individual ions. Any questions on that there? Another important thing about ionic compounds, as we might have touched upon, and really sort of the basis of the reason for it, is what we saw in bonding. Remember that when we saw in bonding with ionic compounds is, in certain cases, you may need more than one of the elements there to allow everybody to sort of complete their octet and get to that noble gas configuration. And that's why when we put together sort of ionic compounds, which is our metals and non-metals together, we always want to make sure that the formula here equals 0. So, if we had obviously a sodium ion and a chloride ion, we simply just need one of each of those, +1 and -1, gets us to 0, which would give us the proper formula of sodium chloride here. When we write the formula for the ionic compound, there is no charge. Although this thing is made up, obviously, of two things that do have charges. So when we do see that formula of NaCl, it actually is telling us that we have a sodium that is +1, and we have a chloride there that is -1. So if you write individually the formulas for the ions, they should have charges. If they're just writing the ions by themselves, if you put them together to make an ionic compound, you should always put them together in the simplest way that gets you 0 in terms of the overall charge. So for example, I think we looked at calcium when we were doing bonding and fluorine or fluoride. So once again, if we just slap these guys together the way they are, we obviously would end up with something with a charge. And really, this wouldn't be good, really, based on the bonding that we talked about. That would only allow calcium really to lose 1 electron and not really get back to the noble gas configuration. So once again, here we do need to balance out the charge. So -2 here balances out the +2 so that we get the proper formula here of no charge and have a 2 on the bottom. So once again, obviously the subscript number goes to the element to the left, and this tells us we have 1 calcium at +2 and 2 fluorides each at -1 gives us -2. And again, we got an overall charge of 0. So the calcium fluoride there, the CaF2 formula, again, has no charge. But once again, if you were asked to write the individual ions here, you do need to obviously include the charges. Any questions on that there? Okay. So here is sort of a table. You have probably a similar one in your book of some of our ions, again, individually here. Hydrogen, lithium, potassium, again, are positive guys, simply just using the whole name. Negative guys, again, gets the IDE at the end of it. So let's talk about ionic compounds and a certain type of ionic compound, and they're sometimes referred to as type 1 compounds. And always when you have a metal and a non-metal together in an ionic compound, really the most important one out of that bunch there is the metal. So it is always the metal that is the most important. And really the sort of location of that metal on the periodic table is really most important. And in a type 1 compound, the metal will be from group 1, 2, 3, or it will be silver, cadmium, or zinc. And what all these guys have in common is they have fixed positive charges. So as we just went through that periodic table, these guys here have basically fixed positive charges. And the nice thing about this is, frankly, as soon as you see that the metal is from group 1, 2, or 3, or again, one of those 3, zinc, cadmium, or silver, pretty much this is how you name all type 1 compounds at that point. You take the whole name of the metal, and the non-metal gets the IDE ending. So that is pretty much how you go about naming type 1 compounds when you see them. So if we looked at the couple that we had up there a second ago, NaCl, first off, we could recognize sodium as a metal, Cl as chlorine as a non-metal, so it tells us it's ionic. We would then turn our focus over to sodium, and we would find sodium there on group 1 of the periodic table, which would tell us it's a type 1 compound and that it has a fixed charge. And really at that point, we just roll right into the name of sodium, and the second guy gets the chloride. If we look at our CaF2 that we saw earlier there as well, once again, we look at calcium, which is a metal, fluorine, which is a non-metal, and that again tells us it's ionic compound. We look at the calcium, which is the metal, which is the most important. We see it's on group number 2 on the periodic table. Automatically tells us it has a fixed charge. So frankly, we just roll into the whole name there of calcium. And then fluorine gets the IDE treatment at the end, and it is calcium fluoride. Now, one important thing when we are doing this type of naming here is this 2 right here has absolutely no effect on the name. So it should not be anything like difluoride or anything like that. There is no prefixes. You could have 400 of those fluorines there and it will still be fluoride at the end. So it has absolutely no effect on the naming if you have more of the second guy. And frankly, it has no effect on the naming if you have more of the first guy as well. So it doesn't really matter. You should never, ever use prefixes in this type of naming. We will talk about where you should use prefixes later on, but definitely not in this situation. So sometimes people like to put those extra prefixes in, makes it sound more chemistry-like, you know, like difluoride or something like that. So you would not do it in this case. Any questions on that there? Okay. All right, so there's our little chart there, like we had earlier, of our common guys. So let's try some here. So why don't you take a second, and why don't you name all these, and why don't you also write the formula for these guys here. Let's do magnesium bromide. Let's do aluminum oxide. Let's do potassium. All right, so names on the left there, and we'll do formulas on the right here for magnesium bromide, aluminum oxide, and potassium nitride. So take a couple minutes. Okay, let's take a look here. So starting with the first one, we have K, which is potassium, that's a metal. Cl is a nonmetal, which is chlorine. So that tells us it's an ionic compound. We would turn our focus to the metal, which is potassium, and we know that it is group number 1, so it has a fixed charge. So really that's all we need. We're going to use the whole name of the metal, which would be potassium. And then our chlorine will get the IDE at the end of it. So this would be potassium chloride. Once again, it is made up of two things that have charge. It is made up of the cation, which is K+, and is made up of the anion, which is Cl- in this particular case. Any questions on that one there? Looking at the second one, we got zinc, which is a metal. We got sulfur, which is a non-metal. So once again, tells us it's ionic. Once again, we focus in on the zinc, and the zinc actually, again, is a transition metal over there, number 30. But it is one of those transition metals that does have a fixed charge. And that means that we could call it a type 1 compound, and we would just use the whole name here of zinc. The sulfur getting the IDE at the end of it, which would be sulfide, IDE. And once again, the cation's formula here would be zinc with a +2 charge, and the sulfur, which is group 6, would be a sulfur there with a -2 charge. And that again is why when we put them together, we just need one of each of them. +2, -2 obviously balances each other out. Question on that? Once again, here we've got Ca, which is calcium metal, Br, which is non-metal, bromine. Looking at calcium, that is going to be group 2. So we could go right into our name, which would be calcium bromide. Once again, the 2 here does not have an effect on the name. The reason there is a 2 there, obviously, is because calcium is group 2. So that is a calcium with a +2 charge. Bromine is group 7, which means there is a -1 charge. So the 2 is there because we need actually 2 of them, again, to balance out the charge and really allow each of them to get to noble gas configuration. In that particular case, once again, no effect on the name or anything like that. In this particular case, we got barium, which is a metal, and a reminder that although hydrogen is hanging out over there on the left-hand side of the periodic table, it is actually a non-metal hydrogen. And our barium is group 2, which means it does have a fixed charge. So this guy here would be barium. And the negative version of hydrogen, which is what we're dealing with here, would be hydride, IDE. Our barium being group 2 is a +2. Hydrogen in this case is a -1. And once again, that is why we need 2 of those guys there to balance out the charge. That is pretty much the time when you do find hydrogen being negative is when it follows a metal. So if you have a metal first and then hydrogen, that is definitely the negative version of hydrogen. Pretty much all other cases, hydrogen is going to be +1. But if it comes after a metal, that is definitely when we do see it being negative. Any question on any of those names there? All right, so to write the formulas here, we're basically just going to take the parts and kind of put them together to get no charge. First off, we see magnesium bromide. So I see magnesium tells me it's a metal, bromine is a non-metal. I go to the periodic table and I see magnesium should be +2 as it is group number 2. Bromine is -1 here, as it is group number 7. So once again, in this case, to get us to 0, we actually need not 1, but we do need 2 of the Br minuses. So now putting these together gives us MgBr2 would be our proper formula there. Question on that one? Aluminum is group 3 on the periodic table, which means it has a +3 charge. Oxide is group 6, which means it has a -2 charge. Now, in this case, we want it to equal 0, so the simplest and easiest way to do that is basically just multiply the two numbers together, gives you 6. So to get aluminum to 6 there, we would need 2 of them. And to get oxygen to 6, we actually would need a grand total of 3 of them. That gives us a -6 and a +6. That would give us the proper formula, I'll go down here, as Al2O3. Now, some people are taught just to blindly do this move. Yeah. And you can also go the opposite way if you have the formula going upwards. And you can do that, but just be careful. It does not work in all the times. Yes. So, you know, if you're good about 93-ish% of the time, then you'd be okay. But it's best to think about it again, balancing it out to 0, not just blindly switching the numbers. There's a number of things that really will not give you the right formula or, you know, sort of the right name if you just blindly kind of go and do the switcheroo. But it does work in a lot of cases, but again, not 100% of the time. Here we have potassium, which is a metal, nitride, which is nitrogen, which is a non-metal. So potassium, once again, going to be group number 1 here. Nitrogen is group number 5, which means it is carrying a -3 charge. So in this case, we actually need more of the potassium to get us there. A grand total of 3 if you want to draw them all out. And basically that is +3 and -3 gets us to 0, gives us a K3N as our formula. Any questions on type 1 naming or writing formulas? Okay, so speaking of hydrogen, since we were just talking about for just a second here, let's talk a little bit about hydrogen, even though technically it's a non-metal. So we'll go back here. So if we do have hydrogen in front, even though it is a non-metal, we oftentimes sort of think about it and treat it almost in naming like it is sort of a metal with a +1 charge, even though technically speaking, it's sharing electrons and all that, but it's sort of named. And the reason for that is it has a lot to do with when it's in solution, it sort of does break apart into ions and creates like acids and stuff like that. So even though it's technically a non-metal, we do treat it almost like type 1 naming. And that means if you had anything where hydrogen was up in front, you know, something like this, something like this, we would sort of follow the same sort of rules. And even though technically speaking, this is all sharing of electrons, this is all covalently bonding, we do sort of treat it in terms of naming like an ionic compound. And we think of this almost as like H+ and Cl-, which in its sort of acid form is what's going on when it's in solution. So basically we would just start with hydrogen, use the whole name of hydrogen, and we would just name the second guy like normal, put the IDE at it. So this would be hydrogen chloride in the gas form. This guy here would be hydrogen bromide. And this guy here, although there is 2 hydrogens, it still will not have an effect on the name. So we would call this hydrogen sulfide, and that is a very stinky gas, which they don't use anymore in 200B, so that's good. So this is hydrogen sulfide is what we call it. Again, even though there's 2 hydrogens in that case, we still just call it hydrogen along the way. So hydrogen, a little bit different in terms of naming, even though in reality, again, all that is sort of sharing of electrons and stuff like that. It is sort of treated almost like an ionic sort of compound in terms of naming. Any questions on hydrogen there? Okay. So then the next type of naming we're going to talk about is also ionic, and it is type 2 compounds. So type 2 compounds also are much like type 1 ionic. Just like type 1, type 2 is consistent of a metal and a non-metal coming together. And once again, like type 1, it is the metal that is the most important one to look at. And this metal will be a transition metal. Are just to the right of it under the staircase. Things like lead, tin, antimony, and that bismuth and that sort of area. So what all these guys share in common is that they do have a variable charge. So, something like copper, for example, can be copper with a +1 charge, could be copper with a +2 charge. Something like iron could be iron with a +2 charge, iron with a +3 charge. So type 2 compounds, unlike type 1 compounds, the metal can have a variable type charge, and it really does sort of depend on what it is bound to in terms of what the charge will be. The good news is you do have to figure out what the charge is on the metal, but the good news is you will always know the charge on whatever it's bound to. So you always know what it is bound to, the charge on that guy. You can work your way backwards and figure out what the charge on the metal is. So the way we name these is pretty similar to how we name type 1. We use the whole name of the metal. We still do the non-metal that gets the IDE at the end of it. The one additional thing that we do with type 2 guys is in the middle there, we do put Roman numerals. And we use Roman numerals to indicate the charge on the metal. So that's really important. This is the actual charge on the metal. Not the total charge, not how many metals there are. It is pretty much if you took one of those metal guys out, what the positive charge would be on it. So if we took something like FeCl2 and we wanted to again figure out sort of what it is here, we would do our normal thing. We would see iron, which is a metal. We would see Cl, which is a non-metal. It would tell us it's ionic. We would look on the periodic table, and we would see iron sitting dead center pretty much on the periodic table in the transition metal region. And that automatically should tell us that this guy could have multiple types of charges. So we definitely know we have one iron, which is some type of charge. We will always know what it is bound to. So we do know that we have Cl, which is group number 7, and that means it has a -1 charge. And once again here, there's not just one of those guys, but there are 2 of those guys present. And that gives us a -2 overall. So since it does need to equal 0, our iron in this case must be a +2 charge. Now, in terms of naming this, we would go with the whole name of the metal, which is iron. The Roman numeral here would be 2, and that is for the charge that is on the metal. And once again here, even though we have 2 of the Cls, it has no effect on the name. It is just chloride at the end. So this would be iron 2 chloride. Any questions on that there? The reason obviously we need to do that is if we had something like FeCl3, this would be an iron, and now we would have 3 of these guys, which would give us a -3. That means the iron in this case would be +3. And this guy here would be iron Roman numeral 3 chloride. So really naming is just telling people, what you're dealing with. And in this case, because the metal could have multiple types of charges, you need to tell people. In this case, we're talking about the iron with the +2. In this case, we're talking about the iron with the +3, and given that. Once again, here in this type of naming, there should be absolutely no prefixes being used anywhere here, so no prefixes at all during this type of naming. Any questions on that there? All right, and then here's some of our variety of charges that we see here. And again, a reminder that type 2 guys sort of also fall in this region below the staircase, even though they're technically not transition metals. This slide is really messed up, but I think it's okay on your handout, hopefully. But there's sort of an older way of naming these type of compounds where we kind of use the root of the name. So, you know, instead of copper 1 here and copper 2, this guy would be known as cupric and cuprous ion. Same thing with something like iron, iron 2, iron 3. This would be known as ferrate, and this would be known as ferrous, and this would be ferric. Sorry, wrong thing. Ferric. So typically speaking, when you kind of go the older way of naming, the guy that has the larger positive charge ends in IC, and the guy with the lower positive charge ends in OUS. We will not use the older way of naming in this class. For type 2 compounds, you should use Roman numerals. So we will use Roman numerals here, not the older way of naming. So make sure you do use Roman numerals for this type. But you will sometimes still see things like cupric, cuprous, ferrous sort of used in places. But again, we will strictly use for type 2 the Roman numerals. All right. So if I had something like, say, this guy here, let's go with PbO2. What would be the name of it? Take a second and write. Okay, so let's take a look. Once again, we see lead here, which is a metal, and oxygen, which is a non-metal. So that automatically tells us it's ionic. When we look at lead on the periodic table, it's not technically a transition metal. It is just to the right. But once again, those guys to the right of the transition metals below the staircase are pretty much treated like transition metals when we're doing naming. That means they can have a variety of charges here. And that means we need to figure out what our lead is here. And in this case, we look at the oxygen. That is group number 6. And that means it has a -2 charge. And there is 2 of them, which means if we add up all the negative charge there, that is a -4 charge for the oxygen, which means in this case, the lead is actually +4. And this would be lead Roman numeral 4 because of the charge. And it would be oxide here. And I do this example for what I talked about before, that people like to do this move. And you might have ended up with lead 2, which would be actually incorrect. So again, as a reminder, it is not always correct to just switch around things. It will not always give you the right things. So make sure you think about it rather than just blindly switching things around. Any questions on that name there? Okay. So let's do some of these here, and let's do some names on those. And let me give you some names to do some formulas. If I can get my thing here in my hand. Let's do chromium 4 oxide. Let's do iron 3 sulfide. And let's do tin 2 phosphide. All right, so okay, let's take a look. So once again here, looking at the first one, we got CO, which is cobalt, which is a metal. We got Cl, which is obviously a non-metal. So once again, tells us it's ionic. We would want to always look at the metals. So we're going to look at the location of cobalt. Once again, we see it in the middle of the transition metal region. So that should tell you it's type 2 that, you know, you need to maybe figure out what's going on in terms of its charge. So you got a cobalt with some type of charge. Again, once again, we do know that the Cl is group 7, which is a -1 charge, and there are 3 of them. So again, if we just draw them all out to make it easier, that is a -3 overall. Then to balance it out, my cobalt here does need to be +3. And that means we can now use the whole name of the metal, which is cobalt. We're going to do a Roman numeral 3. once again, for the charge on each of the cobalts there. And even though multiple Cls, still just going to be chloride at the end of it. Any questions on that one there? Coming here is copper transition metal. And we have I, which is iodine, which is a non-metal. So ionic, once again, the copper being a transition metal, tells us it's type 2. So not sure what the charge maybe is at this point, but we do know that iodine is group 7, has a -1 charge, which means to balance it out, it must be a +1 charge on the copper here. Whole name of the metal, so copper. We're going to insert the Roman numeral to tell us that we are dealing with the copper 1 version of it. And again, our iodine gets the IDE at the end of it, so iodide in this case. So copper 1 iodide. Lastly on this run here, we have a tin, which is a metal. We have Br, which is a non-metal. Once again, the tin is a little bit outside of the transition metal region, but underneath that staircase. So that does tell us it is type 2. So in this case, we do have the 4 bromines here, or bromides, which is -1 each, as they are group 7. So that gives us a -4. So this is going to be +4 here to balance it out. And that's going to give us a name of the whole name of the metal, Roman numeral for the charge, which is +4. And then again, regardless of how many we got going on there, it is going to be bromide. Any questions on the names here on the left? All right, looking then on the right-hand side to write some formulas. This is relatively straightforward on this side because I see chromium and I see Roman numeral and I see oxide, so I know it's a metal, non-metal, which is a ionic compound. And frankly, I see a Roman numeral, which definitely the only people that use Roman numerals are type 2. So I know that's definitely what's going on. And the nice thing about having a Roman numeral is it tells us that the chromium there does have a +4 charge. That's basically what that means, so that we don't have to figure out anything. Oxide, which is oxygen, is group 6. So it has a -2 charge. So in this particular case, we actually need more of the oxygen to get to 0. We need a grand total of 2 of them to get us to -4, which would give us a CrO2 as our formula when we put that together. Any questions on that one there? Once again, iron Roman numeral 3 tells me I have an iron that is +3 in charge. Sulfide is group 6, which is a -2. And once again, the simplest way to put that together is to get to 6 by just multiplying the 2 numbers together. So to get our iron to 6, to balance everything out, we would need 1 more iron. And to get our sulfide to 6, we would need a couple more for a grand total of 3. And that would give us a proper formula of Fe2O3 in this case. Any questions on that one there? Last one here is tin Roman numeral 2. So that tells us we have a tin with a +2 charge. We have phosphide, which is phosphorus on the periodic table, and that is group number 5 over there. And that means it should have a -3. So this is sort of the opposite of what we just did above. We need to get to 6. So in this case, we actually need 3 of the tins to get us this +6. To balance out the 2 of the phosphides to get us to -6. And that would give us a formula here, let's go this way, of SN3P2. Any question on any of those formulas for the names for the formulas, type 2 consideration? Once again, take-home message here, don't do a prefix on any of these, yes? So if you find yourself Roman numerating and prefixing at the same time, you definitely should just put an X on it yourself because it is definitely wrong, yeah, so you should not do that. Any questions on ionic naming so far? Okay, then let's continue on our journey of naming. Here's a little decision tree. Again, type 1 and type 2 are all ionic compounds. They're all metals and non-metals, and whenever you got a metal involved, it's really the most important one in terms of naming is the one that determines how you should name it. And again, that's going to be either with or without a Roman numeral in this case. Let's talk a little bit about polyatomic ions. Polyatomic ions are groups of nonmetals together that have charges so that they are frankly ions. But they are kind of interesting in the sense that they are actually held together by sharing of electrons. So polyatomic ions are actually nonmetals which will actually share electrons together. As a result of them sharing electrons, they do actually have an overall sort of charge. And so they are sort of treated like ions. So if we took something like NH4NO3 here, and if we took this guy and we broke it up right there in the middle, we actually have a couple of polyatomic ions. This guy over here is NH4 plus. That one nitrogen and 4 hydrogens all stay together because frankly, they're sharing electrons and they move around as a group. They never break apart into anything else. And in fact, if we drew our Lewis structure for it, it is this guy right here. All those guys sharing electrons. And that whole entire thing has an overall positive 1 charge. This guy over here is also a polyatomic ion, and that is NO3 minus. And once again, this nitrogen and 3 oxygens all stay together because they are sharing electrons. They move around as a unit, and they have an overall charge of -1. And if we quickly sketch a Lewis structure, it looks something like this, which we might have drew, I think. And that is why, in this particular case, we do get the overall formula of NH4NO3 because, frankly, we're taking something with a +1 charge, and we're taking something with a -1 charge. So just like an ionic compound, we do put it together to equal 0, and we just need one of each of those guys, which is, again, why we have NH4NO3 as the actual formula. Each polyatomic ion has a specific name. This is what is known as the this is what is known as the ammonium ion. This right here is what is known as the nitrate ion. Nice thing about polyatomic ions is, frankly, you just use the name of the polyatomic ion. It doesn't matter how many you have of them. You just simply use their names. And in this case, we would actually just put both names together, which would give us something like NH4NO3 being ammonium nitrate, ATE. So that would be ammonium nitrate by just simply putting both of those guys together. So polyatomic ions are basically have covalent bonding going on, sharing of electrons, but they do possess basically an overall charge. So they are treated pretty much like type 1 and type 2 compounds. The reason for the most part we treat polyatomic ions like type 1 and type 2 compounds is for the fact that that guy right there, the NH4 plus, is pretty much one of the only positive polyatomic ions that you come across. Most of the polyatomic ions are negatively charged, which means most of the time the polyatomic ions end up with a metal. And so what we typically do is basically follow the same rules that we just talked about. If we have the metal involved with a polyatomic ion and it's a type 1 metal, we would just use the metal name and the name of the polyatomic ion. If you have a metal involved and it's a type 2 metal, like we just talked about, with a polyatomic ion, you would use the metal name and the Roman numeral like we did before. So I would say probably 9 times out of 10, you will find a polyatomic ion hooked up with a metal, and you would revert back to the type 1 or type 2 naming that we just talked about a second ago. So for example, if we had something like NaNO3, that would be sodium, which is a metal. That's NO3, which is nitrate, and this would be sodium nitrate. The sodium here would be +1, the nitrate would be -1, which again is why we just need one of each of them in the formula. If we had something like FeNO3, we take a look at this. Fe is iron, which is a transition metal and a type 2 compound. NO3 is nitrate. In this case, we actually have iron. I'm not sure what the charge is, but I do know I have 2 nitrates, which each are -1 charge. That means that to balance out the -2 charge from the 2 nitrates total, the iron here actually would be +2 in this case. And this would be iron Roman numeral 2 for the charge, and nitrate, once again, does not matter how many of those nitrates we have. It has no effect on the name. We just use the whole name of the polyatomic ion. And the 2, again, in the Roman numeral is the charge on the metal. Now, you also see that I did put, which is also very common when you do have polyatomic ions and you have multiples of them. If you have more than one polyatomic ion, you do need to put the parentheses around the polyatomic ion, because if you did not put the parentheses there and you just wrote it without it, you would end up with something like this, FeNO32. And that would mean that we actually have 32 oxygens, right? And 1 nitrogen, which is definitely not what we want. So whenever you got multiple polyatomic ions, you do need to put parentheses around the polyatomic ion and the number on the bottom to indicate how many you have of them. Any questions on that there? So here's a table. I think you have in your notes, and even on I think Canvas, there's a table, and also on our online, there's a table in your book. So, you know, the bad thing is you kind of have to memorize these, and there is a good news in that you can sort of group things together to make it a little bit easier to memorize. So there are certain things that are related to each other. So for example, NO2- and NO3-, for example. This is 1 nitrogen, 2 oxygen with a -1 charge. This is what is known as the nitrite ion. This guy is known as the nitrate ion. If we look at something like SO3 2- and SO4 2-, once again, those guys all stay together. That's in the box. They both have a -2 charge. This first guy with the SO3 is sulfite. This guy is sulfate. So in a group of 2 guys, polyatomic guys that are related to each other, the one with the least number of oxygens in that group of 2 ends in -ite. And the one with the most number of oxygens in a group of 2 will end in -ate. So 8 is usually more oxygen. -ite is less oxygen. Now, there's some other ones that are sometimes a group of 4 that are related to each other. So if you have something like, we'll go here, we'll go here. ClO4-, ClO3-, ClO2-, ClO-. All these guys are related to each other. The only difference is, frankly, the number of oxygens. They each have an overall charge of -1. And we do break it up very similar to what we do with the group of 2. The guys to the right there have the least number of oxygens, 2 and 1. This is what is known as chlorite, ITE. This guy would be chlorite, ITE. You clearly could not have the same name for 2 different things. So when you have a group of 4 that are related to each other, the one with the least number of oxygens end in -ite, but starts with hypo. So that is hypochlorite at the end. We could kind of do the same thing for the guys with the most oxygens on the left there. That is going to be chlorate. And the guy at the end here will be chlorate as well. Once again, we cannot have 2 names that are the same. So in a group of 4, the one with the most oxygens starts with per and ends with -ate. So that is perchlorate, chlorate, chlorite, and hypochlorite is a group of 4. By the way, that is Cl, right, which is a halogen. You pretty much can swap out that halogen for any other halogen, and it's named the same way. So, for example, instead of ClO3-, If I had BrO3 minus instead of chlorate, this would be bromate. So you could swap out any of those guys in there. If you threw an iodine in there, it would be iodate and so forth. So you could kind of swap out the halogens in there, and they're all named very similar to each other. So there's sometimes groups of 4 that are related to each other, sometimes just groups of 2 that are related to each other. Some other things that we do or see on this is, for example, if we have something like CO3 2 minus, that is carbonate. And sometimes we add an H plus to it, and we get something like HCO3 minus, and pretty much we put a hydrogen in front of it. So this is what is sometimes referred to as hydrogen carbonate. And sometimes hydrogen carbonate, just to make life easier, is sometimes referred to as bicarbonate. So bicarbonate is hydrogen carbonate. You also see that with sulfate. If you put an H plus in front of sulfate, it becomes hydrogen sulfate or bisulfate. So you can see that with that as well. Now, the vast majority of polyatomic ions do end in ate and ite. There are some that end in IDE. So like OH minus is hydroxide, ends in IDE. CN minus is cyanide, ends in IDE. Azide, which is this guy, ends in IDE. So there are a few sort of polyatomic ions that do end in IDE, but for the most part, IDE is usually just somebody by itself on the periodic table, a non-metal, but they can be a polyatomic ion. But definitely ate and ide you see a lot with our polyatomic ions. Any questions on that there? So once again, it is sort of a thing where you have to sort of memorize the names and the formulas with the charges. And some people will just remember, for example, all of the eights and know the ites are just 1 oxygen less. Everything else is the same. The charge is all the same. Just drop an oxygen off. Or you could do the ites and know the eights are just 1 oxygen more. So sometimes people will memorize it sort of in that fashion. Any questions on that there? Okay, so let us try some here. Let's do some names for this guy. Let's do that. And let's do some formulas for barium hydroxide. Excuse me. Let's do all right, so names on the left and okay, let's take a look and see. So we have MgCO3. So we do have a metal and we do have a polyatomic ion. Our metal here is magnesium, which once a metal is involved, that's the most important one. That is group 2, which means it has a fixed one. It's a type 1 metal, which means frankly, we just need to use the whole name there, magnesium. And once again, this is our polyatomic ion, which is carbonate. So we would call it magnesium carbonate. The cation here is magnesium with a +2 charge. The anion here is carbonate with a -2 charge. And once again, that is why we just need one of each of those to make the formula correct there. Question on that name. Coming here, next one, we do have iron, which is a metal. We have PO4 3-, which is phosphate, which is a polyatomic ion. The metal is a transition metal. So once again, our cation here, we would be an iron that we might need to figure out the charge on. We do want to look at phosphate, which we do know it is -3, and that actually means we have 2 of them there, I believe. There we go. That gives us a grand total -6 for the negative side, and there are 3 irons, which means each iron would have to be +2 in this case. Gives us +6 all over. That means that the name here would then be iron Roman numeral 2. Again, not 3, but it's Roman numeral 2 because the charge is +2 here. And regardless of how many of these phosphates we have, we just use the whole name, which would be phosphate. Any question on that one there? Lastly, here on the left, we got calcium, which is definitely a metal. We have HCO3-, which is a polyatomic ion. Calcium is group number 2, which means, again, it has a fixed charge. It's a type 1 metal, so that is going to be calcium. And we just want to use the whole name here of this polyatomic ion, so this would be hydrogen carbonate, or you could just bicarbonate it as well instead of hydrogen. And this is made up of a cation that is calcium with a +2 charge, and the anion here is 2 of the bicarbonates, which each have a -1 charge. So again, that's why we need, once again, the parentheses and the 2 on the bottom when we do write the formula. Any questions on any of those names there on the left? All right, on the right, we're going to give some formulas. So we'll approach it the same way. Barium is group number 2, so we do know that the charge is fixed, and that should be a barium with a +2 charge. Hydroxide, if we go to our list there, is OH- in this case. Once again, we're basically going to get to 0, so we got +2 and -1. So we do need not 1 of the hydroxides, but we do need 2 of them to balance out the charge. And that would give us a barium. And because we have 2 of those polyatomic ions, we're going to do a little parentheses and the 2 on the bottom there. Any question on that one there? All right, copper, Roman numeral 2. So the nice thing about that is it tells us exactly what the charge is on the copper, and it is +2 in this case. Perchlorate is one of those 4 that we talked about that are related to each other. It's actually per is the most, and 8 is the most oxygens there. So that is ClO4-. When we put this together, we're putting together +2 and -1. So we actually do need 1 more of these guys to balance it out. And that would give us Cu. We do need parentheses 1 more time, ClO4 and a 2 on the bottom there. Any questions on that one there? In this case, we have ammonium, which is a polyatomic ion, and that is NH4+. We have sulfide, which is not a polyatomic ion. It is sulfur from the periodic table, which is group number 6. In this particular case, we actually need more of the polyatomic ion to balance it out to 0. We need 1 more to do that. That means we're going to open up with parentheses here, NH4, and we need 2 of them, and 1 sulfur there will do us, and we'll end up with NH4-2s. Any questions on polyatomic ions? Again, for the most part, they really do sort of fall back to type 1 and type 2 naming because they will find themselves pretty much hooked up with a metal most of the time. Any questions on any of that? Okay, our journey through naming continues to acids now. Acids are basically substances that produce H+ ions in solution. That's basically what an acid is. It's able to produce this, which is the hydrogen ion in solution, sometimes referred to as a proton as well. Acids are named basically all revolving around whether or not it has oxygen. So oxygen is the major thing that you look at when you're naming acids. So it's really all about oxygen. And if the answer is no, we do not have oxygen, the way that the acid is named is hydro to start with, something ic acid. Now, what makes something an acid is the ability to produce H+, and that also means that for every single acid, the cation is always H+. So H+ is always the cation in an acid. So if we have something like HCl, this is going to be no oxygen. So this would be hydro. The missing part is the negative guy here, chloric acid, where the cation here would be H+, and the anion would be Cl-. If I had HBr, this would again not contain oxygen, so this would be hydrobromic acid. Now, what is the difference between the HCl we talked about earlier and the HCl that we're talking about now, and why is it one an acid and one is not an acid? And it has really to do with the state of it. So HCl, that's for example a gas, is not an acid, and it would be named like we did earlier, which would be hydrogen chloride. HCl, that has the AQ next to it, which means aqueous. It means it's in solution. And it means when you put hydrogen chloride gas in water and bubble it through it, you get hydrochloric acid. And in solution, what happens to that HCl is it breaks apart really into ions that are floating around, and it produces H+ that's floating around, which is why it's an acid, and also has Cl- floating around. So it is the aqueous here that we typically do right next to formulas for acids to tell us that it is an acid, and this would then become hydrochloric acid like we down here. So it is AQ, should be written next to the formulas for acids. And that tells you that it is an acid. So when you write formulas for acids, you should put the aqueous next to it, the AQ. Or if you see something like HCl that has AQ, then it is going to be in the acid way of naming it. If it just says HCl and there's really no direction, you could call it hydrogen chloride. But if it does say name this acid, you would say the HCl is hydrochloric acid, and so forth. Any questions on that there? All right, so if we have acids that do have oxygen, so the answer is yes, it does have oxygen in it. It will then contain one of our favorite things that we just saw. It will then contain a polyatomic ion. And as we just saw, pretty much our polyatomic ions end in pretty much one of two ways. Our polyatomic ion ends in ITE, or it ends in ATE. Yeah. And depending on sort of how your polyatomic ion ends is how you would name the acid. So if your acid does have oxygen and your polyatomic ion ends in 8, the acid would be named as something ic acid. So for example, if I had HNO3, NO3 is nitrate, which means this acid would become nitric acid. There is no hydro here in this type of naming when we have oxygen involved, so just this way, nitric acid. The cation here would be our H+. The anion here would be our NO3-. So once again, +1 -1, which is why the formula looks like that. If your acid does have oxygen and the polyatomic ion ends in ITE. Your acid will be something OUS acid. So if we take HNO2, NO2 here is nitrite, ITE, which means this acid would then become nitrous acid, OUS, where the cation here would be H plus and the anion here would be NO2 minus. Once again, there's absolutely no hydro in this naming. Once again, the hydro is just for things that do not have oxygen that are acids. If it does have oxygen and it's an acid, you should never use hydro with it. Question on that there. So why don't we try a couple here and see. All right, so let's do H2SO4. Let's do H2S. Let's do HCN. Let's do phosphorus acid. Let's do carbonic acid. Let's do hydroiodic acid. All right, names on the left, formulas on the right. So starting with the first one, I see aqueous, I see hydrogen, I see sulfate. So I know it's an acid. I see oxygen in there, so we want to focus on this guy, which is sulfate, ATE, which means this should be sulfuric acid. Any questions on that name there? Coming over here, we see aqueous, I see some hydrogen, I see sulfur there. I do not see oxygen, so this tells me it should have hydro in front of it. So this would be hydrosulfuric, right? The I and the hydro, and this would be acid at the end. Bottom guy here does not have oxygen in it, and this guy would also then be the hydrocyanic acid from cyanide, basically, IDE on that polyatomic ion. So it gets the sort of hydro since it does not have oxygen involved. Any questions on that one there? Phosphorus acid. I know it's an acid. I know that it is OUS, which means my polyatomic ion is ITE. So right there tells me that I am dealing with phosphite, which is PO3, 3 minus. And I know that the cation for all acids is H plus. So again, we want to put this together to equal 0. We would need 3 of the H's. Give us PO3 like that, and a little aqueous symbol. I see carbonic acid. Once again, I don't see hydro in the name, which tells me it has oxygen. The IC tells me that my polyatomic ion ends in 8. Then if I just kind of put those names together, I am now back to carbonate. So that tells me I am dealing with carbonate in this case, and that would be CO3 2 minus. Once again, our acid is always going to be H plus as our cation. We do need 2 of these guys to give us H2CO3, which would be our carbonic acid formula. Question on that one. This acid, I do see hydro, I do see ick, and that tells me, frankly, there is no oxygen in it. So I do know that my H plus, and this would be iodide, and putting those guys together would give us HI. Any questions on acid naming? Nice thing about bases is bases are typically things that make hydroxide, and frankly, they're just named like